Right, it's been a pretty hectic day for me, and I started off with a splitting headache, which hasn't gone away even though I've tried to do some medication for it. So if I stumble a bit during my lecture here, you'll just have to bear with me. I can really feel my concentration isn't quite where it should be, but we'll do an attempt at getting through this lecture in a normal manner. So I'll try to just pace myself so that I don't lose my place too often in this. Yes, also I put a notice out with regards to the CAD lectures this week that I'm switching around with this week and next week, so that we are doing 4-hour lectures this week instead of next week. So that we're going to do full 4 hours, no own time in the CAD studies afterwards this week. And then we'll have regular 2-hour lecture and CAD study afterwards next week. This was due to I have to attend a meeting on next Thursday after the lectures there, so it would have crashed with having a 4-hour lecture. So it was a good way of just changing it around there. I fortunately don't have to move that 2-hour lecture next Thursday. That's what I originally wrote on Fronto, that I would have to move it, but that's not going to be a problem. It's enough with getting it down to just 2 hours instead of 4. So that was everything about the CAD. You had your lab assignments before the weekend, and I think everyone except 2 managed to meet before the weekend, and that's pretty amazing. One of the 2 that didn't meet, we were already aware of that was going to be away. So the two that are missing will have a chance next week to do their lab assignment. Right, then we're going to start here with subsea technology. We have the last appendix on the ROV part. So we're going to do that one, and then we're going to start on the diving part 4 of the appendix. So this appendix here is sort of the process of replacing a flow control module, or FCM as it's abbreviated. And this means that the ROV needs to go to the correct water depth and inspect the hinges on the template protective structure. So this is the I believe in this case it's an over-trawlable protective structure. We'll see that when we get a bit further on into the figures. Then the ROV needs to clean the hinges if necessary and clean the area where they're going to operate. And these hinges are, of course, on the roof of the protective structure, which is covering the subsea processing plant. We will have these sort of lids which can be opened up. And it's the hinges of those lids that are going to be inspected first. And the reason for doing this inspection and cleaning of the hinges is basically just to be absolutely sure that we're going to manage to open these once the module comes down, and we're going to replace the flow control module. Then it's going to open the hatch lock, so the lock that is keeping this one in place. Exactly where this lock is placed is a bit different, but usually it's somewhere on this end. There is a lock that will lock it into place on the protective structure, so that it can't be, if a fishing vessel pulls its trawl across, say from this angle, pulls it across the entire trawl across the protective structure, it won't snag on the hatch and then suddenly pull it open, because the hatch is locked into place, so it's going to stay there. And then the ROV needs to attach a hatch wire. So it's going to, the wire is being lowered down from the surface vessel. I'll do that up here. So we have a surface vessel. It's going to lower down a wire that's going to be attached to the hatch, so that it's not the ROV itself that's actually lifting this hatch. it's going to be the surface vessel that's going to be lifting it up by pulling on this wire. And when the hatch wire is installed on the hatch, the ROV will follow the movement of the hatch as it's being opened, so that the whoever is controlling the winch up on the surface vessel will be aware of how the hatch is moving, so that he will know when he's gotten it fully opened. Once the hatch moves past the sort of 90-degree angle here, so that you get your hatch open to around there, then you can just release the tension of your wire, because it's going to fall over on that side anyway, so that you don't really need to pull any more on it. So that's what the ROV is checking. And once it has been fully opened, it probably has some sort of stopping mechanism somewhere here, so that the hatch will only open to a certain angle. It will stop. It won't fall all the way down and lie flat against the protective structure. Then the ROV will go in and detach the wire from the hatch here. So here we can see the first figure where they are opening the hatch. So the ROV has connected the wire to the hatch itself. It basically says the same. And then it starts opening up the hatch, and it can open it up in several different ways. Basically, they can use pulley systems to get them open. So there are many ways of doing this. But the whole point is trying to get it open to past those 90 degrees, preferably to somewhere around 120 or something, so that when they are releasing it, it's going to go full way open, so that you get 180 degrees opening. So here we can see, sort of from here we have a 3D view of what's happening, while on the next one we are looking at it from the side. So we are looking directly on the side of it. We have the ROV coming in here. It's connecting the wire to the hatch. It's connecting the wire to the pulley system over on this side. So these are actually using pulley systems. So the wire is coming down through a pulley, and then it's going over to the other side, and it's being connected to the hatch itself. So instead of going straight down like this, as I shown there, they are using a pulley system over here. So I'll remove the other wires here. This is in order to avoid having to move the vessel in order to get full opening from it. So they basically have a pulley system here. The wire is going down into the pulley. It's going around the pulley wheel, and then it's going to the hatch itself. So that when they're pulling on this wire, going up here, it's going to go through the wheel, and it's going to put it all the way over. And we can see that the ROV needs to be sort of threading this wire into the correct opening where it's supposed to be connected. So as they start pulling on this wire, then we do have a wire going up here to the vessel. Then we have get it. Do we have it? No, actually, that's the end where the wire is going up on this one. And this was a different system from the one I was looking at. The end of the wire is being connected here. It's not a pulley over there. It's more of a pulley system over on this end, so that when they're pulling upwards on the wire there, it's going to be lifted in this end. This one is going to be tightened up, being a taut string. And as they keep on pulling on this one, it's going to move over the entire hatch. Then when it gets over to a certain point here, they just start releasing wire instead, and then it's going to fall all the way down to 180 degree position compared to the original one. Then the ROV needs to inspect the already positioned guideposts or install temporary guideposts. So if this is a structure where it has permanent guideposts that are placed in there, then that's okay. All the ROV needs to do is just inspect them and see that they function properly. But if it has temporary guideposts, like the ones we have looked at from Imenco earlier, where you can lock them in place and place them whenever you need them, then it needs to install those guideposts beforehand. And then the ROV needs to connect a guide wire. In this case, they need to use 2 guideposts. That depends a bit on the size and geometry of the module that's coming down. If it's a very large module, you might have to use 3 guideposts in order to position it correctly. But usually in the sort of mid-size module, it should be enough with just 2 guideposts, because you need 2 guide wires in order to keep it in one position. And here's the guideposts that are being used in this case. So it's a fairly similar design to the one Imenco has on theirs. They have a ring up top, which can lock it into place, which is operated by the ROV. So the ROV basically twists the ring and locks it into place. And it has locking dogs down here that are going to catch hold of the structure and keep it in place. Then the ROV needs to clean and remove the external tree cap, or ETC, as the abbreviation is. And that's this part here on the structure. So that's something that needs to be removed in order to gain access to the flow control module. Then the ROV needs to clean and disconnect the electrical couplings from the flow control module. And it needs to close off all the valves. And that is done by operating these valve mechanisms on it. And this is I think this is the flow, that's the flow, parts of the flow control module, at least. And then the ROV observes the lowering of the replacement tool. So in this case, the flow control module, it's too large and heavy for the ROV to actually lift it out of the structure. So it needs one of these running tools with an internal elevator system that's going to lift it out of the structure. So the ROV only observes that the tool gets placed in the correct position. And of course, the closer the landing tool gets to where it's supposed to be, the more closely the ROV needs to observe it. So they need to slow down the lowering speed, and the ROV needs to come in closer to get a more detailed view of what's going on. To begin with, when the tool is fairly high up, the ROV can just basically look at it from a distance and see that it's moving in the correct direction, and that it's seems like it's going to land correctly. But then as it closes in, when you have just a couple of meters left, then the ROV needs to move in close and check that the guideposts are going to be entering correctly and everything like that to make sure that they get a smooth landing of the replacement tool. And then the ROV assists during the pulling of the module itself. So the pulling will be basically when the ROV is operating the replacement tool in order to pull the ROV module out of the structure. So basically lifting it with the internal elevator system. So in this case, it's we have the manifold connectors and stuff there. Here is the running tool up top, and it's grabbing onto the flow control module. and I've forgotten to put in the animations here, but then the ROV is going to clean the electrical and hydraulic couplings on the template itself, so on the structure where the flow control module is. Then it's going to assist during the installation of the new flow control module and external tree cap. Then it's going to connect all of the electrical couplings and disconnect guide wires and close and lock the hatches again. After that's done, the valves need to be open and the flow control module needs to be tested to see that it works properly. Yeah, that was everything. So basically, what happens now is the reverse order of what happened before. So that if we just start moving ourselves backwards, going backwards on our presentation here, we are basically going to get the correct order of doing things in it. So that was everything on this one. It's just to give you a certain... That was on the wrong picture. It's just to give you a certain overview of how a typical ROV situation is when you're doing an operation with an ROV. That what the ROV in fact is doing is quite a lot of sort of menial tasks where it's just connecting stuff, cleaning, and disconnecting stuff, observing that everything is being done properly, while the heavy lifting itself is being done by the winches on the surface vessel and also by the running tool itself. So basically, if this had been in shallow waters and you've had a diver down here, the diver would have been doing the exact same tasks as the ROV does in a situation like this. So then we're going to look at diving and divers, and this is one of the early diving systems that were in use, where they basically just trapped air inside a very heavy steel cylinder, and they lowered it down onto the shoulders of whoever was going to perform work. So it's an opening in here, so there is air for him to breathe in here, but there is an opening of water here. So if for some reason he needs to bend forwards or something, air is going to escape from this one. So it's very important with a primitive system like this that he stays upright. So whenever he needs to reach down to get something, he has to bend his knees and keep his upper body upright at all times. If he doesn't, air is going to escape and he's basically going to drown in there because it's not really safe in that one. But that's really old systems like they did it to begin with. Then they improved them somewhat and they created diving bells where they got larger systems where they could sit inside. So here we can barely see the surface of the water inside here. So there is just a little bit of water inside the bell itself. Then the rest is air under pressure. And considering that these guys are just sitting in here with air under pressure, they can't really go all that deep because they're going to be sitting in this. And usually when they did diving in old times, it was basically in order to perform construction work in dock systems and stuff like that. So it was usually very shallow water, and it was along the shore that they were doing it. Maybe to build a bridge or something, so they were putting down the foundations of the bridge pylons and stuff like that. So usually they were working down to 20, 30 meters depth at a maximum when they were doing stuff like this. And as you can see here, they've actually got a barrel filled with air that's releasing air into here just to get some fresh air into this diving bell. So really amazing systems that they tried to get working. Then they continued developing it. This was over the course of hundreds of years that they were developing these stuff. So the new developments didn't really happen all that fast, nowhere near as fast as they're happening nowadays with technology. But then they started getting to the point where they could have a system where they had a hose going up to the surface, delivering air to the diver, and he had everything contained in a helmet, so that he no longer needed to have this diving bell with him or anything like that. He could move around more or less freely, so long as the hose was kept operating and giving him fresh air. And what they did to stay at the bottom of the ocean when they were working was to have like really heavy boots. So they usually had some sort of like lead boots that they were using, and those were heavy enough to allow them to walk around on the ocean floor. If they had used regular boots there, then the weight of the gear that they were needed to breathe wouldn't be enough to keep them down, so they would be buoyant. They would be floating upwards instead. So they needed to add extra weight, which is the same as divers have to do today. They usually use lead weights in belts around their waists, and they adjust these to get become almost neutral in water. So that was just a very quick history of diving. There is more written in the compendium, but it's more for it's not the history part that we are here for. That's just to give us a brief knowledge of what has come before. So now we're going to look at some of the physics that are in diving, because we are talking about gas here, and we are talking about pressures, and we're also talking about human lives. So it's quite important to get these things right in a working environment. So first off, we'll start looking at the gases themselves when we are handling diving gear. And we should already be aware of that the air that we are breathing in regularly, it consists of approximately 78% nitrogen. It is 78 point something, so that it's fairly close to 79. And we have approximately 21% oxygen in the air that we're breathing, and the oxygen is what we need in order to survive. We have to have the oxygen, or else we're going to suffocate. Our bodies won't function without oxygen. And we also have almost a percentage of argon, the noble gas, and that's what's making up the 1% that's missing between the nitrogen and the oxygen. And since argon is a noble gas, it's not going to react with anything. It's just going to stay a gas no matter what. If you start mixing oxygen, nitrogen with other substances, you will get reactions when you're doing it, so that they will connect to each other. If you mix in oxygen and carbon, you're going to get carbon monoxide or carbon dioxide or anything like that. But with argon, it's just going to stay argon. It's not going to connect with anything else. And then we have this very small percentage of carbon dioxide that we are breathing in. And then, of course, we have hundreds of others, different types of gases that are in very minute percentages in the air we breathe every day. But this is what we mainly need to concern ourselves with when we are talking about breathing gas for divers. Now we'll start looking at the nitrogen. And it does not contribute to the processes in our bodies. So nitrogen is not something that we need to survive. And this means that we can remove nitrogen from the air that we're breathing without it having any consequence for us. We, of course, need to replace it with something else, which we're going to look at in a while, because we can't replace it with oxygen, because too much oxygen is actually bad for us. We need to have the perfect amount of oxygen. But with the nitrogen, we can actually remove it completely without it being a problem to our bodies. And actually, if we get too high of a partial pressure of oxygen, then that will give us a narcotic effect. So it will basically be like you're intoxicated if you get too much nitrogen in the air that you're breathing. And then we'll start looking a bit at oxygen. And oxygen, as I mentioned earlier, it is highly necessary for life. So we really do need it. Another problem with oxygen is that it sustains combustion. So for anything to burn, it also needs oxygen there, except for very certain circumstances, very specific situations where you can actually have combustion without oxygen. But those are way beyond the scope of what we're looking at here. And it is, since it is necessary for the process of life, we have to have it in the breathing gas. And when we're looking at the air that we're breathing regularly, which is 1 atmosphere of pressure, 1.01 bar approximately, then oxygen, as it says here, it has a partial pressure of about 0.2 bars, which is connected to the percentage of oxygen in the air. So that's what partial pressure means. It sort of means with the gas that we're breathing at the pressure that we're breathing it, so that if the deeper down we are, the higher pressure we have, we need to know that the partial pressure of oxygen will remain approximately 0.2 bars. So that if you look at it from a percentage point of view, the oxygen needs to stay like this. Because if we get too high of a partial pressure of oxygen, then it's going to lead to oxygen poisoning, which very quickly will lead to death. So we really need to keep it at the correct partial pressure. And when that's said, having that partial pressure at 0.2 bars, or 20%, if you look at the pressure, 20% of the pressure, that's basically it's still toxic to us. Oxygen is still toxic to us, but it doesn't have any long-term effects. Sort of, it is necessary for us to live, but it's still dangerous for us. But within the ranges that they've found of partial pressure that we can use in the diving breathing gas, then it's not going to have any long-term effects for us. So that we can deviate somewhat from the 0.2 that we're normally breathing. So we can deviate a little bit from it without it having any long-term effects for our health. But as soon as we go past a certain limit, then we're going to start having problems. To begin with, it's going to be temporary problems that can be fixed by just returning the partial pressure to the correct one for our bodies. If they go too far, it's going to become oxygen poisoning, and which can lead to death, basically. Then, of course, the argon, the noble gas, it has no effect on us. So we could replace the 78% of nitrogen with all argon, so that we were breathing almost 79% argon and 21% oxygen. Wouldn't be a problem. It wouldn't have any effect on our bodies. Then we have the carbon dioxide that we're breathing, which we all know that we don't really want carbon dioxide. But it does serve a purpose when we're breathing it. So for a certain very small percentage, it does serve a purpose in our breathing. And it acts as a regulator for our breath, so that we are breathing in the correct tempo. One of the positive sides with carbon dioxide is, of course, that it does not sustain combustion, so that if you replace oxygen with carbon dioxide, then you basically can't light a fire. There is no oxygen to sustain the fire. And it's highly dangerous for a diver to have too high concentrations of carbon dioxide in the breathing gas. Because it starts off with getting an increased breathing, because we're getting too much, so it's regulating our breathing too much. So we increase the amount that we're breathing. Then we are producing more carbon dioxide ourselves. So we are adding to the problem. So it's sort of an evil circle there that we are sort of making it worse. It will give us a headache as we go along. We will start to sweat. Then we will start to feel like we're suffocating. And we will have an increased danger of decompression sickness, which is something that we're going to look at later on, which can be also fatal if it is severe enough. Then we're going to look at a couple of other gases that are being used that are not part of our regular everyday atmosphere. They are part of it, but they are even less than the carbon dioxide in our gas, so they're not usually listed in what we're breathing normally. So we have helium, and it's the same as argon. It's a noble gas. It's not going to react to anything, but it has less atomic mass than nitrogen. And that means that it's lighter, there is less weight in it. And that means that if you're breathing helium instead of nitrogen, it means that your lungs have to use less energy in order to push the air out of them and then suck in new air. So that replacing nitrogen with helium, that's a positive. And probably most of you have either heard others do it or tried it yourself with sucking the gas from a helium balloon and listening to your voice. It gets radically different. You get this high-pitched Donald Duck type voice. And for the saturation divers who are going down to very deep waters, they breathe helium and oxygen, which often means that when you're listening to radio clips from where they're talking to their operators on the vessel, and they're sitting in their compression chambers talking to each other, they have these helium voices when they're talking. So it sounds really strange. And if I remember correctly, the operators for the radio, they actually have to learn to hear their voices all anew, because they can't really make out what they're saying with these very affected voices. So that it's a whole new learning process of figuring out what people are actually saying when their voices are that much affected by helium. And probably you've heard, with regards to helium balloons, you shouldn't do that really, because it can actually suffocate you. And that's of course because then you would be sucking in pure helium. You wouldn't get any oxygen down into your lungs. But with the case with saturation diving, you are mixing oxygen and helium, which means that you are getting oxygen down, so it's not dangerous to keep breathing it. And it's the most used gas when you are doing saturation diving. And of course, as I said, then you combine it with oxygen, which is completely necessary. One problem you do get with it is that you have temperature issues. So it gets cold, basically because helium has a very good thermal conductivity. So it sort of, it sucks doesn't suck it, but the body heat that you're producing gets conducted more easily through helium than it does through nitrogen, so that you are losing body heat quicker when you're breathing in a helium-oxygen atmosphere. And helium, it diffuses easily through materials. So when we are talking about diffusion, you learned about this in your materials class, but just to do a refresher, that is basically when the molecules of the gas are able to sort of pass into the molecules of a material and sort of move through them. And then it depends on what kind of concentrations you have on which sides of the material. So that if you have a high concentration on one side of the material and a low concentration on the other, then it's sort of going to be pushed through the material. So even though you have a steel plate, you can still have diffusion going through the steel plate. So even though steel seems to be completely solid, when you get down to the atomic level and the molecular level, it's not really solid, so that things can pass through it. And helium does that fairly easily. And it can result to problems with equipment because you get helium sort of saturated into materials when you're using it. Then we also have water vapor, which is common in our air also. It's not listed as one of the main ingredients in the air we breathe. But it can cause problems with diving, such as you get fog on your viewing ports, in your helmets and masks, so that you can see what's happening on outside, and you can't actually put a finger up there and try to wipe the fog away. That's not going to work. Then you're going to let loads of water into your mask, so that's not something you can do. And the water vapor can also freeze inside the air hose, so that you're basically obstructing the airflow through it. So as it freezes, it's going to make the cross section more and more narrow. So you're basically throttling the airflow coming in, so that you will have problems breathing. And it also affects your body temperature, because it's going to help cool down your body, which means that you're going to need to produce more body heat from your body, using more energy. But another problem is that if you have too little water vapor, it's going to become an irritation both in your mouth and in your throat. So basically a very bad case of a sore throat is what you're going to get. So you're going to feel like you need to drink water at all times in order to keep your throat moist, is the correct word I'm looking for. Before we continue on, we're going to do a 15-minute break. Okay, so we'll start up again. So we've been looking at the different gases that we use when we're diving, and also that we use in everyday life as we breathe. But now we're going to look a bit at the laws of physics that are the most important with regards to diving. So earlier we've looked at the different hydrodynamic forces and the laws of physics that we have there. Now we're going to look at, for an example, pressure. Pressure is going to have quite an effect on our divers. And the pressure, when we are measuring it in water, is that we have an absolute pressure in bars, which is the depth of seawater in meters divided by 10 plus 1. That's going to give us how many bars there is at a certain depth. And the whole point here is that we have the absolute pressure. And that is the plus 1 that we're putting in here. That is from the air in our atmosphere. So that's the atmospheric pressure that we are experiencing right now at approximately sea level when we're ashore. And that 1 bar there that we're putting in, that is basically, if we took a column of air, so we have a cross-sectional area of, I think is it 1 or is it 10? It's 1 square centimeter. And then we extend this cross-section from sea level and all the way up into space. Then all of the atmospheric gas that we have inside that column, that's going to amount to approximately 10 newtons in force. And when we put those 10 newtons across the cross-sectional area, that's going to give us approximately 1 bar, or the 1 atmosphere that we are talking about, which is 1.01 bar. But in this case, we're not really concerned with the 0.01 part in it, so we're just saying that it's 1 bar. So that's the atmospheric pressure that we have on land here. And then we are adding, for every 10 meters of seawater that we for every meter of seawater, so it's going to be, we're dividing it by 10, so it's going to be every 10 meters of seawater, we add another bar. So if we have 10 meters of seawater, we divide it by 10, that means we have 1 extra bar. So it's going to be 1 plus 1. So then we have 2 bars when we are down at 10 meters depth. So this means that a regular scuba diver, which is doing it in their spare time just for fun, diving around, they usually can go down to, I think the first certificate they get is down to 30 meters, if I remember correctly. I haven't done this myself, but I have a couple of friends that have. So it's down to 30 meters, and then they have to do an additional course in order to be certified to go down to 50 meters. So at 50 meters, they would have 50 meters of seawater divided by 10, that is 5, plus 1, so then they have 6 bars of pressure when they're down there. 6 bars of pressure, that's approximately the same as the water pressure in your tap at home. When you're opening your tap and the water is coming out into your sink, that's approximately a 6 bar pressure, because that's the usual pressure that is used in the water pipes around everywhere. So it's not really all that much pressure when you're looking at it like that. But according to my friends that actually do scuba diving, you can really feel it on your body when you're down there. So, and probably you can feel it yourself if you go into a pool and you just dive down to the bottom of the pool. A Olympic swimming pool, I can't remember if it's 5 or 10 meters deep. I think it's just 5. But with 5 meters in depth, you are only adding 1/2 plus 1, so you have 1.5 bars. And you can still feel it pushing on your body. So you can really feel it when you're doing it. So I've often wondered what these divers that are working down at 300 meters, how it feels for them when they are being basically squashed like that. So again, we'll do a little example here. We have 20 meters of seawater in depth. We divide it by 10. That gives us 2 plus 1, and we have 3 bars. So it's just to show us that it's a fairly easy calculation, this one, and it doesn't make sense with the units either. So we have to be aware of that. We are going to get our answer in bars, but we are putting in meters of seawater there, so that it doesn't make sense in a unit kind of way, because this is basically an empirical formula to use. So it's not based on actual mathematics and units per se. It's based on the experience. We know that it increases with 1 bar for every 10 meters of seawater that we go down. It does come from physics, of course. You can sort of pull this out and show it with your physics, go into hydrostatic pressures from your fluid mechanics, and you can show it perfectly, not a problem, but this is sort of a very easy formula to remember when you're working with it. We also need to think about temperature when we're going down there, because as we all know, water is often used to cool stuff when we need extra cooling, and considering that we are placing hot human bodies down into cold water here, we are going to have quite a cooling effect on them. So we need to know a little bit about temperature when we're working with this. And with temperature, we have something called Boyle's Law. You know it from your thermodynamics, not by the name of Boyle's Law directly, but you know that you can put up pressure times volume and have it be a constant, so that if you have a constant temperature, you will have a constant pressure times volume. Which means that if you are increasing your volume, you have to decrease your pressure. If you are increasing your pressure, you have to decrease your volume, of course. We have something called Charles' Law, and that's when we have a temperature that's actually changing. So now we've Boyle's Law, that one looked at a constant temperature situation. So for an example, when you get to a certain depth, the water temperature is usually around 4 degrees Celsius. So there you would have a constant temperature situation. But for an example, if you're in the Caribbean and you're going to start diving there, then up by the surface you're going to have pretty warm waters, and then as you move down, your temperature is going to decrease further and further towards approximately 4 degrees. So then you need to look at Charles' Law a little bit with regards to pressure and volume, and then you have the gas constant and the temperature, because we are now looking at the breathing gas itself. So we are calculating the pressure of the not calculating, but we are working with the pressure of the gas. We all remember from our thermodynamics that if we were talking about the water itself, we would have an incompressible fluid, so that the volume would stay the same. So here we are talking about the gas that's being breathed. So if we combine these two, we can set them up like this, so that we have pressure, we have volume divided by temperature, and then we can have one state equal to the other state. This is just repetition from thermodynamics, basically. We have something else called Dalton's Law, and this is the one that you haven't seen in thermodynamics earlier, which is the one with partial pressures. So I've already spoken a bit about it. If we get nitrogen or oxygen, too high of a partial pressure for nitrogen or oxygen, or for that matter carbon dioxide, then we are going to experience different negative states in our body, intoxication-like states, suffocation, stuff like that. If you go too far, you are risking death. And that's a part of Dalton's Law here, where you have a total pressure, which would be the one that we are calculating for the absolute pressure, which is how deep we are going in the water. Because if we are doing saturation diving, you need to you need to compress the breathing gas to the same pressure as the water is going to be outside where you're going to be diving. So for an example, if we are diving down to, let us say, 100 meters. So if we're diving down to 100 meters, we have 100 divided by 10. That gives us 10 plus 1. Then we have 11 bars of pressure. That means that our P total is going to be 11 bars. And then we need to know that our oxygen partial pressure needs to be around 0.2 bars in the partial pressure. So we know that we need to put in quite a lot more pressure in the helium side of our scale there. So we need to compress and put in quite a lot more helium in order to keep the oxygen down to 0.2 bars, because we have a total volume of 11 instead of 1 bar as we have up here. And basically the partial pressures is just adding together the partial pressure of each gas, and then you're going to get the total pressure in the end. We have something called Henry's Law, where the amount of gas dissolved in a liquid at a given temperature that is proportional to the partial pressure of the gas. Now this is relevant because basically our bodies are mostly liquid, and the air that we breathe, the oxygen in the air that we breathe, it diffuses through the tissue in our lungs and into our bloodstream. And our blood is a liquid, so it's being moved around our body as a liquid. So the gas is diffused into the liquid. Did you have a question? No. So that we have, it doesn't only dissolve or diffuse into the bloodstream, it will also dissolve into the cells of our body, because those are also mostly liquid. So that if we are being, that is basically why they're calling it saturation diving, because you are making sure that all of the liquid of your body is being saturated with the gas that you're breathing. And this means that we need to be aware of the temperature of the liquid and the gases and the partial pressures there, because there is a link between temperature and partial pressure. So that if we change the temperature too drastically, we are also going to change the partial pressure quite a lot, and then you can suddenly move away from the 0.2 bars of oxygen in partial pressure. You can suddenly move into the danger zone if you don't watch the temperatures that you're working at. We also have Archimedes Law, which we have already looked a bit at, which is the buoyancy of an object, so that we have the buoyancy being equal to the weight of displaced fluid, which is of course something the divers have to take into account. That is why they have these lead weights around their waist to keep them fairly neutral in water. If they are going to be swimming around when they're working, they want to be neutral. If they are working down at the seafloor, they usually want to be not weightless basically, but have some weight. So they want to have additional weight on them, so that they are being forced down onto the seafloor and they can walk around. Still, they usually don't have the same kind of gravity as we have here on land, so that it's going to feel a bit more like they're on the moon or something, so that if they jump up, they are actually going to go quite high up instead of the regular height that we're used to. So it's a bit different kind of movement, but still they can move around the seafloor as if they were on land, if they're just moving slowly enough and not using too much force when they are doing stuff. So then we're going to look at the physiology of our bodies a little bit, and diving medicine, how this affects our bodies, because all of these laws of physics here, they're fair enough. They are regarding the gas that we're breathing and the water that's surrounding us if we're diving. But now we're going to start looking into the biology of our body, what's actually happening when we're diving. So for our breathing, it's going to be affected. And if the pressure in the breathing gas is less than the pressure in our lungs, basically so that if we have a higher pressure inside our lungs than what's outside, we are going to have to use more energy in order to suck air in, because we actually need to suck it in. Well, we need to create, with the muscles in our lungs, we need to create a vacuum in our lungs so that we are forcing the air into them. If we have a slightly higher pressure in our surroundings than what we have inside our lungs, then basically all we need to do is just open up our throats and everything, and the air is just going to flow in by itself, so you need to use very little energy to breathe. So that depends a bit. You need to make sure that you have the correct pressure on your breathing gas so that it's going to be fairly easy to breathe. Because of course, if you need to use quite a lot of energy just to breathe, then you're going to have less energy to concentrate on the task at hand that you're going to do, and you're going to have less energy for your muscles to move and actually do physical labor. And usually when divers are working, they're doing very hard manual labor. So it's more like construction work. So they're doing heavy lifting, they're doing welding in difficult positions where they really have to bend and twist and keep their positions. And it's a pretty hard job to do. It requires quite a lot of strength. And if you're then sort of wasting much of your energy just by breathing, then you're going to have a hard time doing your job. And when we're diving, we have the problem of creating dead spaces inside our bodies, which basically means that we will be having pockets of air trapped in different parts of our bodies, because usually most of our bodies is liquid. So in our guts and everything is just liquid. We don't have any gas in there. But we do have gas, air-filled pockets in our sinuses, in our ears, and also in our lungs, of course. So that we do have areas where we usually have air that can be trapped. And probably everyone, when riding an airplane, they've experienced having this popping sensation in their ears. And that's because the channel between the ear and your throat or your sinuses, it has been closed off by the pressures, so that the pressure has dropped enough for your tissue to basically just close the access between them, which means that you have pressure that is trapped inside your ear. And that's why it can sometimes actually hurt when you have changes in your pressure then. And that's why you often hear that popping sound. That's when it opens up. That's also why it often helps to do yawning motions or chewing on something, because then you're moving your muscles a lot and you're opening it up. This is extra important when one is diving, because you really don't want to sort of block off these pockets and trap some of the breathing gas in there, because then as you're being lowered down, the pressure outside is going to increase and increase and increase, but the pressure inside your ear or something is going to stay the same. And that's going to be very painful after a while, and in the end your eardrums can collapse and everything, and that's really painful. I haven't felt it myself, but from what I gather from other people's experiences, it's a very painful thing. And of course, we also do get air in front of us, because here we have the mouthpiece of the mask, and the mask itself is also filled with gas. And when we are breathing now, it's not only the gas inside our bodies that we're trying to move out and then suck in new gas, we also have to move what's trapped right in front of us. Because in a room like this, we have motion in the air around us, so that's what's moving our atmosphere around, so that we are constantly getting fresh air to breathe. But if we have a closed-off mask in front of us, we are the ones that need to move that air and get it into the respirator system, so that we can pull in new air from our tank. And this also means that we are going to basically be creating a resistance against breathing. So it's going to be a frictional force with the breathing gas moving through hoses and through valves and everything like that in the breathing gear. So that's going to, just like in hydraulics, we are basically creating friction when we are moving the gas through it. And when pressures increase, the density of the breathing gas also increases. And since the density increases, this also means that the weight of the gas is being increased. And that means that it's going to be require more energy to breathe, which is why we prefer using helium instead of argon in the breathing gas, because argon is heavier. The molar weight of argon is heavier than the molar weight of helium, so that by using a lighter gas, we can sort of counteract the effects of pressure and increase density. And we also have varying amounts of oxygen consumption, because it is highly dependent on what kinds of tasks that we are performing. And this you can sort of relate to if you are out exercising, you are running or something like that, where you're really using your body. Your muscles will be needing more oxygen, which means that you have a higher oxygen consumption. So whenever you're doing something that increases your pulse and you get heavier breathing and you're really using your muscles, you're going to need more oxygen than if you are just sitting still and just waiting for something. Then you're going to use quite a lot less oxygen. So it varies how much oxygen you need when you're moving about. And human beings can only survive 2 to 5 minutes without oxygen. Of course, there are examples where people have fallen into ice-cold water and basically drowned, been under there for 30 minutes, and the paramedics have been able to resuscitate them back to life once they've gotten them out of the water. There are stories like that, but unless you have immediate access to emergency help, 2 to 5 minutes is usually what it takes before you are actually dead. Whether or not someone is close enough by to actually help you and save you and get you back to life, start your heart working again and getting air into your lungs, that doesn't really matter if you're down at 500 meters, not 500 meters, but 300 meters depth and working there. That's not going to be an option. No one can save you when you're that deep. So 2 to 5 minutes is as long as it's going to work. This will mean that you will get hypoxia, lack of oxygen, and it can lead to a sort of drunken state, and then fairly quickly you become unconscious. So you're basically not, you basically pass out, and then your body will just shut down while you're passed out. This is also what happens on an airplane. If you have a pressure drop in an airplane and these masks fall down, this is the reason why you are supposed to put your own mask on first before you help others. Because this hypoxia stuff, that can happen really fast, especially at very low pressures. So in an airplane, if the pressure drops below the atmospheric pressure, so below 1 bar, then it's going to go even faster. So then you will have less than 2 to 5 minutes. I saw a clip once on YouTube where they were testing this in a hyperbaric chamber, and they figured out that 15 to 30 seconds, if you're up at 30,000 feet, which is regular flying height, it might be as little as 15 to 30 seconds before you are actually starting to fall unconscious. So you will almost fairly immediately start walking into this drunken state, and if you don't get this mask on yourself, then you will fall unconscious very quickly. So that's why don't put the mask on your children first, put them on yourself, then put them on your children, because it doesn't really help your children if they can breathe and you're fallen unconscious beside them. Then you can't help them anymore. So that's why it's really, really important. I'm going to put a link in, I think when I put this one up, to actually a YouTube video, it isn't a part of the curriculum or anything, but it's a very, very nice one with regards to this, with hypoxia and stuff. And although it's related to airplanes, it is still the same that divers can have troubles with. So, and if we get too much oxygen, as I've already mentioned, it's going to become poisonous for us. So it's really not good for our bodies. And we also need to remove the carbon dioxide that we're exhaling, because that will also become poisonous if we get it in too high concentrations. And you get fairly similar symptoms to the hypoxia part, where you feel that you're in a sort of drunken state, and then you fall unconscious after a while. Then we have decompression sickness, which I mentioned briefly a bit earlier. And what happens with decompression sickness is that we looked at Henry's law a little bit earlier, where we were talking about the gases diffusing into liquids. And our body is mostly liquid, so the gas that we're breathing, when we are increasing the pressure of the gas that we are breathing, it's going to sort of be forced into the liquid of our bodies. So we're going to have quite a lot of gas that's trapped inside our bodies. It's the same principle as a soda, where we have carbon dioxide that has been diffused into the liquid by increased pressure, which is also why you get this fizz when you are opening a soda bottle. It's because there's a higher pressure inside there, and that's what's trapping the carbon dioxide inside the liquid, and that's why it starts bubbling. As soon as you open up the cork, you are releasing the extra pressure that's in there, and then the carbon dioxide starts diffusing out of the soda water. And just to draw a parallel to the soda there, if you have your body acting as the soda water with gas diffused into it, and you change your pressure too quickly, then you are going to get bubbles inside your body, just like inside the soda. And that's what decompression sickness is. It's basically the gas being forced to diffuse out of your body too quickly, and it's going to form bubbles, instead of ending up being diffused into your bloodstream and then into your lungs and out of your lungs, so that you will be exhaling it. If you're doing this correctly with changing the pressure at the correct pace. If you're changing the pressure too quickly, then it's going to be forced out, and then it's just going to basically form bubbles inside your body. Which means that we have our blood transporting all of these gas molecules to our lungs, and that means that we are going to have bubbles forming inside our blood, and also in our tissue, of course, because not all of the gas will have had a chance to move into our bloodstream yet. And this means that we can have these bubbles moving around, and they can get stuck in our joints, close to our nerves and stuff like that, and they're going to put pressure on our nerves. And whenever you have pressure on one of your nerves, it's going to be painful. And that is why often decompression sickness, one of the symptoms is that all of your joints are hurting, so that you have painful joints everywhere. But it can also, you can get bubbles that are large enough to actually block the blood flow. And if you get bubbles blocking the blood flow up to your brain, you're going to die really quickly. But also for your other vital organs. If you're blocking the blood flow to your other vital organs, you can die fairly quickly of that also. So that's the really dangerous part with decompression sickness, is that you can basically die without being actually aware of that you were in a danger of dying. Much like getting a blood clot that's moving around and possibly blocking your blood flow. So the symptoms are pains in your joints and muscles, and some people actually get paralyzed. So the bubbles will actually cause paralyzation, so they will block off the control nerves from your brain and to your limbs, so that you will become just like someone who is paralyzed by an accident or something like that. You can become deaf because you're basically blocking off the function of your ears, so you can't hear anything. And you can go unconscious. So if you're starting to block off the flow to your brain, you're getting too little blood up to your brain, you'll go unconscious from that. And then, of course, if you get further than this, you'll end up dead, most likely. Another problem we have with diving is body heat and heat loss in general. And normally, up here on land, we lose our body heat when we are breathing, so the air that we are breathing out is warmer than the air that we sucked in. And we're also losing body heat through our skin, which is, of course, why we are wearing clothes, because we need to trap the body heat close to our bodies. And the temperature of the gas that we are breathing in, it directly impacts the body heat that we have. You will feel this if you are in we don't get that cold winters here, but if you're in further up north in Norway and stuff like that, you can have winters where you have 20, 25, maybe even 30 degrees minus, so that the air that you start breathing then, unless you have something in front of your mouth that is actually sort of warming up the air before you suck it into your lungs, it's going to be painful in your lungs because it's so cold and it's sort of sucking the heat from you. And that's the same thing that happens with the diver, because when you're down at a certain depth, you have everything around you is at a constant temperature of approximately 4 degrees. That's going to make it pretty cold. It's not so cold that it's going to be painful from the cold or anything like that, but it's going to suck the heat from your body pretty quickly. Which is one way of getting around this is that they're not using a dry suit when they're diving. They're using a wetsuit, but it's not open to the seawater, so it's not seawater that's inside the wetsuit. It's actually warmed water that's being pumped down from the surface vessel through a tube. So they're getting warm water into their suits, which helps them keep that temperature better. And one of the things for a diver is that it's actually that individual diver's resistance to cold. So how much cold can that person tolerate? That is often what defines how long periods that person can work while diving. And that basically means if you're going to be able to work for an 8-hour day, an 8-hour shift as a diver, you have to be resistant to cold in some shapes. You've probably seen people in the winters here in Norway walking around in shorts and t-shirts. So people who aren't really much affected by cold. It's not that they really don't feel it. They're still getting as cold as they look, but it's sort of that they don't really, it's not something that bothers them. And that's the fact with the divers also. If you're not really bothered with being cold, then you can work for longer stretches of time as a diver. Because that's the best way of sort of controlling your own body heat while you're a diver. Is just, have I been cold for a very long time now? Am I really freezing? Then I might have to think about going up, because you don't want to end up in hypothermia, so that you're getting too cold. That would also be potentially deadly if it goes on for too long. Yeah. You said the heating process of the diver is from the surface. Yeah. Usually it's coming from the surface vessel. Is it adiabatically Usually it will be when they're diving, saturation diving and stuff like that, they're in a diving bell, which is fairly, it's the same principle as the primitive ones that we saw in the start. So that one is lower down from the surface vessel, and the hot water is basically coming down the umbilical of the diving, along with the breathing gas and stuff like that. So it's coming down to the diving bell, and then it's going through a thinner hose, basically, out to the diver. So, of course, the deeper down they are, the further the water has to travel through this hose. So it's going to cool down. So of course, if you have a really long distance there, you might have to increase the temperature with a couple of degrees on the water. So it's something that has to be adapted to that particular situation. If it's a short distance from the vessel and down to where the divers are working, you won't have that much heat loss through the hose while it's going down. So it's something that needs to be taken into account in the operation of it. So the guys sitting in the control room on the surface vessel, they're the ones who have to make sure that the water that actually reaches the suit of the diver has the correct temperature. And yeah.
If it gets cold, how is it drained?
This is water that is circulating, so it's going back to the ship to be heated up again. I'm pretty sure that you're using fresh water on these, so it's not ocean water that's being heated. But it could be a possibility. So for an example, if in the diving bell you had electrical supply there, where you can supply quite a lot of current, you could use electrical heating of seawater in the diving bell unit, and then you could pump it out. So that is a possibility. But I think it depends a bit on how you want your systems to work. So, but usually it's supplied from the surface vessel. Yeah. Equalization of pressure in body cavities. I talked about this a little bit with the ears and our sinuses and everything like that. Which is basically that they have free access to the breathing gas and the tissues of our bodies, which can't be compressed, surround them. And when we are changing the pressure very quickly, we can trap pockets of gas in these body cavities, which, again, like on the airplane, you can get uncomfortable pressure on your eardrums. Your eardrums can burst, which is very painful. You can burst blood vessels inside your ears, so that you will actually start bleeding from your ears. If I've understood correctly, the bursting of the eardrums is far more painful than the bursting of blood vessels, but of course the blood vessels look quite a lot more dramatic when you have blood coming from your ears there. So if you're quickly descending or ascending while holding your breath, you can actually collapse your lungs or burst them, depending on which way you are moving. So if you're quickly descending, you can collapse your lungs because you are increasing the pressure on the outside, and it's going to just compress the air that you have trapped inside your lungs. And if you're quickly ascending, the air inside your lungs will have quite a high pressure, and you are ascending, and the pressure is going to decrease around you. And if you keep holding your breath, it might actually burst your lungs. And that's a very serious injury. So will most likely cause death, but it depends, of course, on the situation a bit. This isn't really a problem for professional divers, but more like free divers, the ones who dive without any breathing gas or anything. So I think the world record is some 60 or 70 meters, where they are basically holding onto a weight. They're just holding their breath and holding onto a weight while they're sinking down to a certain depth. Then they release the weight, and then they swim up again. So it's sort of an extreme sport doing this stuff. So that's more of a problem in those cases. Another problem we can have is gas poisoning, which we've talked about with carbon dioxide and oxygen and even nitrogen, which can become poisonous in too high partial pressures or too high partial pressures. There is also something that's called high pressure nervous syndrome. And it basically means that the diver will have problems concentrating, and they can become nauseous. And basically becoming nauseous and vomiting while you're in a diving suit, that's really not something you want to be experiencing. They can have problems remembering stuff, and they start sort of tremoring, so that their bodies will start shaking uncontrollably. And we don't really know what causes this, but it seems that certain people are susceptible to this syndrome, so that basically, if I remember correctly now, it doesn't say so in the compendium, but if I remember correctly, if ever a professional diver experiences high-pressure nervous syndrome, he is automatically retired. So then he can't work as a diver anymore, because you never know when you're going to experience the syndrome again. So that is something that can return. Some people will never experience it when they're diving. Most divers are of that ilk, but every now and then a diver will suddenly start experiencing this. This is actually in a film from early 1980s or something. I can write up the name here. This is just on a side note. If someone wants to watch a fairly good science fiction movie, it's The Abyss. I think it's 1984 or 1985 it was made, but it's James Cameron who had the made the original movie, and it's basically a subsea oil rig. So it's not it's a manned subsea oil rig they have. And something happens, and there are aliens in the picture and everything like that. But one of the guys that are down there, he starts experiencing the high-pressure nervous syndrome. So, and it even gets explained pretty well in the movie. So it was just a tip if you have nothing to do on a Saturday evening, then you can watch that movie. So we'll stop there for now, and we'll continue on Thursday.